now. Is that working? Good. Can make a start. So my name is Christopher Orrit. I'm a Research and Development Manager at CRV. And I'm going to talk about quite a hot topic at the moment, which has been methane in the animal agriculture sector. But a little bit of background to CRV. CRV is the national cooperative of the Netherlands. So they celebrated their 150th anniversary last year when they established the herd book. And they've been quite leading in their research collaborations with different research institutes around the world. A little bit about what we do. So obviously we're most well known for our semen, but we offer, depending on the market, different insemination services, heat detection services, milk recording services, certainly in the Netherlands and in New Zealand, genomic testing, and evaluation services. So one of the things that our cooperative offers is the national genetic evaluation for the Netherlands. That's why we generally have a research interest in the breeding value development space, and applications and data. So part of our research and development strategy is to look at the different aspects of sustainability. So one of the most important aspects of sustainability is the economic. You know, it is really important that our processors and producers have a workable economic model to deliver high nutritious milk into the market. So that's probably the most important aspect for us in terms of sustainability. The social aspect, as a strong European organization, then the role of our dairies in terms of the management of the infrastructure of our countryside is really, really important. And also the environmental. So that's probably the topic that we're going to talk a little bit about today. But first of all, genetics gets a bit of a bad rap. I see a lot of geneticists in the audience here, and I probably don't need to say that to them, but genetics is really, really important from a dairy economics perspective. So this graph here on the right shows the average milk production of a cow in the Netherlands in the last 30 years. That's the blue line on the left-hand axis. The red line shows the genetic merit for milk in that same time period. So when we look at the amount of milk that we've produced in that time period extra, it's about 3,000 and a bit thousand litres. When we look at the genetic merit that's changed in the same period, it's about 2,000, just over 2,000. So 3/4 of the additional value that was delivered through that two dairies in that 30-year period came from genetics. And we often hear lots of little stories about heritabilities and people misunderstanding them and how it's only a small fraction. But when we look at what's actually delivered through dairies in extra production, it's probably the single largest driver of profitability that you can use. And it's really important, not just from that economic perspective, but as we look at the way that we're trying to improve agriculture around the world, it has the ability to touch a lot of the sustainable development goals that have been set. So not just making sure people don't go hungry, but how we curate the environment around us and what we do to manage those natural resources. It's got a lot of press, but the methane challenge that we have is there whether we like it or not. And not just from a government perspective, but from a consumer perspective. When you don't have to go very far on social media to find people attacking the agricultural industry. And the challenge for us is how we show that our commitment to the environment while continuing to deliver in terms of nutrition and food security. And methane is perceived as a bit of a problem. You know, it's the single largest part of methane, the methane that's put into the environment, the single largest aspect of that comes from ruminant digestion. It's huge here, both in America and internationally. So the graph on the right shows the FAO estimates of the average heard around the world, the average production environment around the world. The one on the left is from the Environmental Defense Fund here in America and shows the US methane emissions by cattle and pork. But it's really important to keep it in perspective. So this shows the total. So they use this phrase carbon dioxide equivalence because not all gases are the same. So carbon dioxide, methane, they have a different impact on the environment. But it's that little sector there that we're talking about. And that's why I think it's really important to be part of the conversation and to defend our industry, because we're often expected to bear the brunt of the solution while not being that big a part of the problem. But we don't necessarily influence policy by ignoring it. And so being part of the conversation, acknowledging some of the challenges that we have, is often a better way to defend the industry than just pretending the problem doesn't exist. And that's how it became an opportunity. Because when we see, governments haven't decided how they're going to necessarily deal with the problem. There's a few ways of looking at it in Belgium and the Netherlands, but from an international perspective, there isn't a one-size-fits-all solution. But what we have seen is the processors making their own mark on what sustainable dairying means. And that's created opportunity for dairy farmers. So if you look at people like Fonterra, who are offering additional cents on a pound of milk for those dairies that are producing milk in a sustainable fashion, it creates the opportunity to exploit that in order to improve profit margins. And we do see also dedicated product lines from different producers around the world that cover, you have here in America that neutral one is a local one, which is supposed to be carbon neutral. And processors pay extra for that milk. So, methane. Go a little bit, knowledge nut teaching, we're supposed to do the whole thing. So, have a little bit look about what methane is, how it's produced. So, methane's produced in the rumen. It's caused by the breakdown of carbohydrates in the rumen, which create volatile fatty acids, carbon dioxide, and methane. Some people a little bit surprised that 98% comes out the front end. It's only about 2% that comes out the back end, which is a little bit different to humans. But that rumen's awesome. And it's probably one of the strongest assets that we've got. Because what it allows us to do is to take low quality roughage and convert that into highly nutritious food and lots of different products throughout the supply chain. About 86% of the food a dairy cow consumes is not fit for human consumption. And cellulose, that one on the far right, which we can't really digest at all, makes up about 40 to 50% of all the chemicals on the planet. It's a huge proportion of the world, and cows can convert that into something that we can use. And they use bacteria, fungi, archaea, which are weird little things that think of them like bacteria, and protozoa. And that's what does the conversion. And the problem is with the acetate and the butyrate that the cow produces, these volatile fatty acids, which get transported into the bloodstream, and that's what becomes the food that the cow eats. There's this little bit of hydrogen that's produced as a byproduct. And when that hydrogen's in excess, some of those archaea, the methanogenic archaea, convert that into methane. And that's what we see emitted in the cow at the front. It goes into the environment, but it's really short-lived. So it takes about 12 years through natural processes for methane to become carbon dioxide. And that carbon dioxide then goes back into what we know with the plants and the photosynthesis and become cell walls and sugars within plant systems. But it only takes 12 years. And that's pretty short. When you compare it to fossil fuel burning, so coal, oil, gas, that takes about 1,000 years because it's a stock gas. That coal formed over millions of years, and then we release it in a second through burning, and that goes into the environment. Whereas methane only takes about 12 years. And this is the other challenge with policy making, is that it's seen as tractable, which means that policymakers think that we can do something about this. They don't want to deal with the transport things. They don't want to tell people they can't drive their cars. They don't want to tell people they can't go on planes. So methane is a quick fix. And so making sure that we're part of the conversation and making sure we have the balance in the goals that are being set when it comes to how we deal with the issue is a really important part of our sector. And we can't do it without dairy. When you look, and there's lots of reports about, what we should eat either in Europe or North America. When we look at food security in Africa and Southern Asia, people should be eating a little bit more animal products in order to deliver that food security that they need. And it's an important part of the solution. And it's acknowledged as an important part of the solution. The United Nations acknowledge it, FAO acknowledge it. It is a huge part of how we are going to feed the world. So there's a balance. And it's a really, really important balance. Because dairy is essential in how we feed the world. And that means that we need to keep doing it. There's no two ways about it. There's no discussion. Dairy is an important part of how we're going to solve food security problems. And there's lots of things we can do to make it better. There are dietary factors. We know that they've heard of Bovaer and their pilots that they've been running to reduce methane in dairy cattle. There are other factors about feed intake and how we manage cows and the rumen microbiome. But genetics is going to play, just like it always has done, a huge role. So this is the normal thing that certainly the geneticists in the room do on a day-to-day basis. But to get here, where we have a trait, we want to do something differently, we want to change something, we want to breed for what we need, then that's where we want to be before we incorporate it into our breeding goals. In order to do that, we need to collect some data. We need to understand what we're dealing with, and the phenotypes, as we call them, are tricky sometimes. Feed intake was the obvious example of one that was really expensive to measure and was a really challenge to get enough records to do a good genomic prediction on. And methane is no different. It's a real challenge to measure methane. It's a bit of a pain. It just sort of blows off into the environment. You can't capture it. There's been a number of ways that people have developed to measure the methane emitted by a cow. The gold standard is really the respiration chamber. You get a cow, you stick it in a box, it's all airtight. You can measure exactly how much methane is coming off and going, it's good. There are some more high throughput ones, so I'm not going to go into too much detail about these. SF6 tracer methods, the little gases they pump into the rumen. Two I'm really going to talk about is the green feed and the sniffer. So green feed's great. They actually have, in terms of their measurement, you get the total amount of methane that the cows emitted. It's a little box. It feeds concentrate. The cow's trained to go in, eat the concentrate. It measures the total amount of methane in that time period that the cow emitted. And it's measured in grams per day, and it's a really, really, really good measure. It corrects for the background levels. It does all sorts of little things. It's a little bit expensive. In terms of how many cows you need like one green feed for every 30 cows. They are quite expensive, over 100 grand. So it's a little bit expensive to run, and it's a little bit expensive to measure. Sniffers are good. They're cheap. They're high throughput. You put them in a robot. They measure the concentration of methane, the parts per million in the atmosphere. But you can only put it in a robot. It's not a great measure of how much total methane, because you only get the concentration. There might be lots of it at low concentration or a little bit at very high concentration. You don't really have that all worked out. So we started measuring. That was the thing that we started in, well, CRV started, I wasn't there, in 2018 with 3 research programs that we've got going on at the moment. The Climate Smart Cattle Breeding Project, which was with Wageningen University in Friesland-Campina. And that set out with the aim of measuring 10,000 cows on the sniffers, and was part of a PhD by Anouk van Breukelen, who was published last year. We also do some work in New Zealand, so quite a lot of our bulls have been measured on a green feed that we have in the bull barns, and the daughters of these bulls were born a couple of years ago. They'll be milking soon, and we'll be able to have a look at the correlations between bulls and their daughters and how it all works out in terms of the heritability. And then in 2021, we installed 3 green feeds, who was our chairman's farm, Vitsa, and they've been collecting data for a few years now. And they kind of existed as separate projects. The 2 that we had in the Netherlands, the climate smart cattle breeding and Vitsa projects, were 2 different things. Collected lots of data. It is to date the world's largest methane data set for the genetic improvement of dairy cattle in the world. But the big breakthrough came when we managed to bring these 2 things together through quite a strong genetic correlation. So think about it like somatic cell count and mastitis. They're strongly related, a little bit less than this genetic correlation that we've got here, but we use somatic cell count to improve mastitis outcomes. And only reason we can do that is those 2 things are linked. And this was the great thing about this discovery that we had a couple of years ago, is that we can use the sniffers, which are great in terms of volumes of data that you can generate through it, and link that to the data that we've got on the green feeds. So we get the gold standard, the total flux of methane measurement that we get from cows from the green feeds, and we get the volumes of data that we need to generate a genetic evaluation from the sniffers. So we did that. In April this year, we released a breeding value for methane as part of the National Genetic Evaluation. And that's on this grams per day, which is the gold standard when it comes to how much methane is a cow actually emitting every single day. So we've got quite a good genetic standard deviation. This describes the amount of improvement that you can make from selecting on it. So if you have a cow with 104 breeding value for methane versus a cow with 100 breeding value for methane, there's about 31.9 grams per day. If you've got 1,000 cows and you account for the fact that methane has a 30-something times the environmental impact of carbon dioxide, that's over a ton of carbon dioxide equivalent a day that you can reduce. So a little bit about those measurements. So I started talking about this gold standard, which is the total amount of methane that a cow produces a day. It's about 400 to 500 grams on average, and it's literally all day she produces 450 grams, say. These cows also vary in their milk production. And one of the key metrics, I'm going to talk about the differences between breeding values that we use in KPIs. One of the metrics a lot of processors are using now to look at the sustainability of their products is the grams of methane per liter of milk. So this is a measure of how green the milk is. It's used by people like Fonterra, people like Friesland Campina, to assess the environmental efficiency of an entire dairy. And it's a good KPI. Don't get me wrong, it's a good KPI because it gives you the green value of the milk. But KPIs are great for setting targets. They're not great for achieving them. So we've got the 2 measurements. We've got the methane production, total methane. We've got the methane intensity, the methane per kilogram of milk. And I just want to focus on that methane intensity a bit more. Good news is that that's heavily correlated with milk production. We know we've done a great job in improving the grams of methane per kilogram of milk over the last 20 years because we've been selecting for milk. If you've got more milk, then you dilute the methane by the amount of milk you've got. Great. And we've made huge improvements. Every year, there's like 0.32 reduction in the amount of methane per kilogram of milk. About 13% reduction in that period. Challenge is Go on. That milk's unfavorably correlated with the total amount of methane a cow produces. So if you breed a cow for more milk, she will need to consume more to produce that milk, and that one cow will be producing more methane per day. So there is an unfavorable correlation between milk production and methane. So if you look at the graphic on the right, you've got the methane intensity, that CH4 per kilogram of milk, and that goes up. It got better. We improved it. We said that. We saw that on the previous slide. The problem is that the methane totally produced per cow goes down. That's bad, which means that emitted more methane. And that's a big challenge for us. It depends how we want to address it. But the thing is that if you're a processor, you buy from 100 herds, and those 100 herds make, let's say, 10% more milk in a period, but they also produced 5% more methane, you've increased your environmental footprint. Which means that the only option, really, is to lose 5% of the herds that you were buying from. Because otherwise, you've just increased your methane. So it's one of the answers to, well, one of the outcomes to this problem is that processors need fewer and fewer dairies to meet the amount of milk that they need and meet their environmental commitments at the same time. It's one of the reasons that we see some governments around the world cutting the amount of dairies in the national herd, because they know they have to achieve these goals, but those cows are making more methane because they're producing more milk. So there are some solutions. So we'll go back to the cow and her 400 kilos of milk a day and acknowledge that she has some production. And we learnt this when we did feed intake. So when we did feed intake, we know the cow doesn't need all that feed to produce the milk. There's a bit that she needs to produce the milk, and there's a residual component that's attributable to that cow. Some cows produce more methane, genetically. There's lots of reasons why they might be their control over the microbiome. There might be giant elephants that just need to consume lots of food, produce lots of methane just to stay standing every day. About 5% of the feed, 5% of the mature body weight of a cow she needs to eat a day. That produces methane. So there are ways that we can compartmentalize the methane an animal produces and associate the exact amount of methane she produced for production from the amount of methane she produced because she's inefficient. So, and we're familiar with this. It's complicated, I know. People have a hard time with residual breeding values. We see it in Feed Saved. Here in the US, we see it with Feed Advantage, which they have in the UK. There's this compartmentalization of feed and methane, and we have a bit of a hard time understanding it. But it is why she's inefficient. And that tells us which cow to breed from to improve that efficiency. And that's why we have these feed safe maintenance, breeding values, so we can select cows that are more efficient and have less environmental impact. And the great thing about it, it's now completely uncorrelated to any of the traits. We've taken the correlation out, and we have something clean that we can select for that won't impact production. Because the problem with that grams per day breeding value is if you select directly for it, then the production will go down. If you correct for production, then you can control the two things independently and improve the environmental outcomes. So, last thing. What does that mean for the future? So these are the trends that we have, the different breeding values. And this was the output of that climate smart cattle breeding research program at Wageningen University. So we can reduce the methane intensity by 42% by 2050 with the addition of selection of methane. So if you look at the little, can I do this? Go on. Yeah, that one. This is where we were going. That was the trajectory in terms of our improvement on that methane per kilogram of milk for the last 20 years. If we add in the methane breeding value, we can get there faster without harming production. So it is possible. This is a huge 39 grams, isn't to be sniffed at. Again, across 1,000 cows, that's over a ton of carbon dioxide equivalent a day. And I like to think of it like this. This is one of my parting thoughts. If you're trying to reach, sorry for the metric, I'm sure you can convert it into freedom units. But if you're trying to reach 4.5% butter fat and achieve 40 kilos a day, you don't just have your hand on the milk button. If you really want to impact your fat percentages, you have to have your hand on milk and you have to have your hand on fat. And it's the same thing. When we're trying to impact methane intensity, we have to have our hand on the milk button and we have to have our hand on the methane button, because then we have the control. You can't just cross your fingers, breed from milk, and hope that you're going to get a favorable outcome. If you have a fixed target, then you need to be able to control those two things independently. And by incorporating a methane breeding value into the selection goal, you have that additional control. Huge shout out to a few collaborators. So Larissa Zatuni, who was supposed to be here today, she wrote most of this presentation. Yeah, most of this presentation. So she's my head of sustainability research over at CRV. Big background in sustainability of agricultural infrastructure. Our collaborators, Wageningen University, Friesland Campina, who he supported with the Climate Smart Cattle Breeding Program, Re-Livestock, which is an EU Horizon project that we were a part of to look at the bigger world picture, and the team from the Animal Evaluation Unit and Wageningen University. And I'm hoping that we're now at about half an hour. Thank you. Wait for the microphone. Wait for the microphone. Wait for the microphone. Maddie, go
front. So Chris, you mentioned that a cow standing there.
Can you hear him?
Can you hear me?
Okay. Yep.
Okay, so Chris, you mentioned if a cow just stands there doing nothing, 5% of her feed?
3%, 3%, between 3 and 5%.
You have nothing in there and selecting for a smaller cow. Great, I have a cow who is producing the same amount of milk but less in her methane, but if she's 2 meters tall, 3 meters tall versus 1.5, she's still wasting a lot of methane just standing there.
Yeah.
So why wasn't that included?
Because
why didn't you include
we wanted to leave that in. So big cow, if we accept, and this is contentious, that big cow's bad, then we want to breed for smaller, more efficient cows. So we only correct for fat and protein corrected milk, because the extra methane that she's included as part of a maintenance should stay in the breeding value so that we drop it. So we correct for milk. We don't expect that most dairy farmers, when they look down a bull proof and they are looking for which bull to select, this isn't going to be their first option. We're assuming a little bit that they've already looked at milk, they've already looked at fertility, they've already looked at lifespan, some of the big win ones, they're already going to look at. So they've made their decision about what production level they want to achieve, and they might look at this one at the end. So that's why we correct for fat and protein corrected milk, but choose to leave, like we did for feed intake. So our feed efficiency valuation in the Netherlands is also not corrected for maintenance, which is different to what the Canadians do.
So if I really want to make strong improvements on methane, should I do more on smaller body size, more on feed efficiency, or your residual methane?
Well, this is the thing, it's only 3%. The maintenance, in terms of the amount of food that cow is consuming, and there's a strong correlation between feed intake and methane output. It's only a small fraction. We get, the milk is like 20% correlated to methane. The body weight, a little bit less. So that's why we choose to leave it in. We made the conscious decision to do that because, according to our friend Mike Coffey, big cows are bad. Thank you. Any more questions? One at the back.
Hi. What kind of heritabilities and things like that did you get? Repeatability, heritabilities. What did you get for that?
So, 4 grams per day, about 0.37 was the heritability, which is really, I mean, pretty good for a trait. For the sniffer component, for just the sniffer component, I think it was 0.15. But they're published. If you look, we published that in an interval bulletin. If you look at the interval bulletin, then for each lactation, for each breakdown, you see all the heritabilities quoted. Any more questions? In that case, thank you very much for your time.